In this video, I'm going to give you 4 important tips that you need in answering your AS Physics Paper 3 question number 2. But not only tips that I'll be giving you, but also applying the tips in various past year questions. And I need you to stay along with me until the end of the video because I need to make sure that you really understand all the tips given and also applying all the tips in answering your AS Physics Paper 3, question number 2. But before doing so, please do subscribe to my YouTube channel for more important tips to be discussed for and the way of making physics once hard to easier. So let us get started. Tip number 1, measurements. What is this? Everybody knows that physics experiments is about measurement. Are you sure this is about the tip number 1? Yes, I'm very sure. So I want you to see this. I am going to give you some example here. So one of the past year question, this is one of the past year question. The diameter of a cylinder A is D, as shown in figure 2.1. Measure and record D. So when you see this type of question, automatically you would take this out. What is this? This is your CM rule. So all you need to do is just to do your measurement. It's not that hard. You just place your CM rule on the exam paper and you can measure your D. But the hardest part is to make sure how you record your final readings of D. So remember what I told you in my previous video, which also I would attach in the description. Please do have a look at the video. I do mention that whenever we are using apparatus to do our measurement, so all the readings recorded must follow the absolute uncertainty of that measuring tool. So I'm using a meter rule here. So therefore, after I measure the D, I need to make sure, okay, before I record the value or the rating of D, I need to make sure what is the absolute uncertainty of my meter rule. So the absolute uncertainty of the meter rule, if you don't know about absolute uncertainty, never mind. It's really not a problem, not an issue here. So you just recall, what is the smallest division of the meter rule? Easier, right? So the smallest division of the meter rule is 0.1 cm because each scale is 0.1 cm. That's the smallest division. Or we call it as sensitivity of the meter rule. Very easy. Just put a plus minus here. That becomes the absolute uncertainty of your meter rule. So meter rule has 0.1 cm as its absolute uncertainty. Make sure that you record your D value in terms of 1 decimal point. All the readings must follow the decimal points of the absolute uncertainty of that apparatus. So make sure that you put your D value in terms of 1 decimal point. I'm sorry, not significant figure, but decimal point. Remember, this is 1 dp together with the unit, which is cm. Very easy to gain that 1 mark. But I also want you to beware with this. You need to look at the mark or the marks allocated as well. For example, determine the period T1 of oscillations of the bulb. Period is oscillations, period of oscillation is very important in paper 3. Right? Whether we are talking about paper 3, question number 1, or paper 3, question number 2, both are very important. So I have something here. This is definitely not pendulum, but at least I have something to show you. So to measure the period, you don't just displace it and then let it go and 1. And then you time. Okay, you see, whenever, because you are conducting the experiment by yourself, this is individual experiment. How are you going to displace it? And then press the stopwatch at 1 time. So most of the students, they did this. I want you to look at me carefully here. So you displace it. And then when you let it go, you press your stopwatch. And then 1. That's it. So most of the students, they just let it go and let it swing freely and come back, and that's it. That's the period. This is super duper wrong. You shouldn't do like that, because when you first let this pendulum, you just imagine that this is a bob. So when you first release your bob, there's a large air resistance acting on the bob. So what are you supposed to do is that you just displace it at small angle, let it swing freely by itself for a few oscillations. Take your time. Then once you notice that it has already swing it in a stable way, so you just press the stopwatch. 1, 2, 3, 4, 5. Maybe you want to take 5 oscillations, so that is up to you. So you need to put down time taken for maybe 5 to 10 oscillations. That will do. 5 oscillations. Okay, so this is T1. Make sure that, because this is 2 marks, 1 mark will be given to repetition. So you need to make sure that you record twice, repeat your reading. Hey, remember what I talk about stopwatch? I do talk about stopwatch in one of my video when I discuss on paper 3, question number 1. Please refer to the description below. So for that video, so stopwatch, I put it in terms of 1 decimal point. So all my times are in 1 decimal point due to my human reaction error. So then to calculate the period, you need the average first. Find the T average. So this T average is the time taken for 5 oscillations, the average time taken. And make sure that, let's say T1 is, for example, T1 is 20.1 second and T2 is 20 second, for example. So your T average is 20.1 plus 20 second divided by 5 oscillations. No, divided by 2. So this is the T average. It's not period. So 20.1 plus 20 divided by 2. So you get 20.1 plus 20 divide 2, and you're supposed to get 20.1 second. I put it in, when you calculate your T average, make sure that this is calculated data. So calculated data, you have to look at the significant figures of your raw data. So I have 3 significant figures for both of my raw data. So that is the reason why I put 3 significant figures for my T average. So to calculate period T1, very easy. Just take your T average divided by the number of oscillation. Let's say 5 oscillation. So 20.1 divide 5. So 20.1 divide 5, and you get 4.02 seconds. That's the period. And period is the calculated data, because I'm using my calculator to do my calculation. So look at the significant figures of your raw data. This is 3 significant figures. So therefore, your period 1 must be 3 significant figures as well. So my answer is 4.02 seconds, and we are done. So tip number 2, estimation. You are asked to estimate the percentage uncertainty of certain stuff. So what are you supposed to do? Bear this in mind first, put bear in your mind. So paper 3, question number 2 is an experiment that they ask you to conduct with lots of errors and uncertainty. That is also one of the reasons they never ask you to plot the graph, or else your points will be scattered everywhere. So you couldn't plot the graph seriously, right? So therefore, you have to bear this in mind. When it is full of errors and uncertainty, your measurement is really, really inaccurate. So let us look at one example here, example 3. So measurement of the rebounded height of a ball. I give you a diagram. So you are asked to assemble the apparatus like the one that I showed you here. Let's say a ball that they give you normally is a ping pong ball, because it's a light ball, not a heavier ball, or else how to rebound, right? So the surface is a flat surface. This is the table. So you are asked to drop a ball from a certain height, for example, maybe at 50 cm mark on a meter rule, and then you're just asked to drop the ball, and then you are asked to see the height of the rebounded ball. So ask yourself, this is the meter rule. So normally we use a meter rule. Oh, I'm sorry, this is a cm rule, but I want you to imagine this as a meter rule. So normally we use a meter rule to measure something that is stationary. So if I want to measure this eraser, I just put it on the meter rule and I get my measurement. And if I want to measure this length of this pen, I just put it on top of my meter rule and I do my measurement. So the pen, the eraser are not moving, but now you are asked to use the meter rule to measure something that is removed moving very fast. So at one point, you have to look at the maximum height of the ball, and the other point, you have to look at the value, the scale on the meter rule, the reading on the meter rule. So how do you do that, right? So nobody is fast reaction. You don't have. Plus, with the human reaction time, do you think you will get a very accurate reading? I don't think so, because I couldn't get it as well, right? Nobody can do that. So therefore, follow my step. I'm giving you this step-by-step thingy, so I hope that you could follow it step by step. So first, you determine the absolute uncertainty of your measuring apparatus. Hey, look at this diagram here. I am using a meter rule. So what is the absolute uncertainty of my meter rule? So absolute uncertainty is the smallest division of my meter rule, which is plus minus 0.1 cm. I'm done. Then second step, use your logic sense, because this is about logical thinking to judge how big the error is. You see, I have to look at the rebound height of the ball, but the ball is not close to the scale on my meter rule. It is still far apart. How am I going to use my imaginary horizontal line to check the maximum height and link it to the scale on a meter rule? Don't you think so? So I think the error is quite large, right? So then increase the absolute uncertainty of the measuring apparatus. You cannot put it as 0.1 cm anymore. So you should increase it. So increase it maybe to 0.5 cm if you think that the error is not so large, or maybe 1 cm. Bear in mind, absolute uncertainty can only be in one significant figure, so that is why I put 1 cm. Maybe you should increase it to 0.5 or to 1 cm if you think that it is too large, depending on the surface on your lab as well. So, and depending on the ball that they gave you. So just use your logic sense and never put your absolute uncertainty as the smallest division of that apparatus. This is absolutely wrong. So when they ask you to estimate the percentage uncertainty, they're asking you to estimate the absolute uncertainty first. And you cannot put your absolute uncertainty as the smallest division anymore, because this question number 2 is full of errors. So you need to increase your absolute uncertainty. So if I want to find the percentage uncertainty of the height, rebounds height, I just put H. So it is delta H over H times 100%. So delta H is the one that you want to see, which is the absolute uncertainty of your measuring apparatus. If I put 0.5, then it is 0.5 divided by the H value. You read it from the measuring apparatus and times 100%. And bear in mind, absolute percentage uncertainty must be in 1 to 2 significant figures only. That's all. And tip number 3, supporting a suggested relationship. You're asked to support. For example, it is suggested that the relationship between T and D is T squared equal KD, where K is a constant, right? So you have to explain whether your results support the suggested relationship. So one of the mark will be given to the calculation of K. So you're asked to measure T twice and D twice and then find the value of K. So let's say I have already found my value of K. I have 2 K values because I have 2 T values and 2 D values. So K1 is 0.0393, K2 is 0.0464. So how do you gonna do about it? So how do you calculate the percentage uncertainty to see the percentage uncertainty of K to check whether your results support the suggested relationship? So let us look at the step-by-step method. So first of all, you find the percentage uncertainty of K. So how do you find it? Percentage uncertainty of K is equal to the difference between the 2 K values. So whether it's K1 minus K2 or K2 minus K1 divided by smaller K value times 100%. So in this case, okay, my K1, so let me check. My K1, percentage uncertainty of K, my K1 is 0.0393, which is smaller. So I take the larger value of K, 0.0464 minus 0.0393 divided by smaller K value, 393, and you times 100% after that. So I'm going to do it right now. 0.0464 minus 0.0393 divided by 0.0393 and times 100%. So this is the one that I got. Percentage uncertainty of K that I calculated is 18%. So then compare with the limit of experimental accuracy. So it actually depending on a logic sense as well. So if your limit of accuracy is within 10% and my percentage uncertainty of K is 18%, then this is out of the limit of experimental accuracy. If your limit of experimental accuracy is 20%, then this is still within the experimental accuracy, limit of experimental accuracy. So for this kind of question, there is no right, there's no wrong answer. So it depends on your conclusion and it depends on the limit of experimental accuracy that you have set. So if it is within the limit of experimental accuracy, then you should support the relationship. If it is out of the limit of experimental accuracy, then you do not support the relationship. So it all depends on you. And the last tip number 4. Wow, this is the hardest part to score full marks for question number 2. Don't you think so? Limitations and improvements. So what is limitations? So most of the students think that limitation is just normal problem that you face, right? It is true in a way, but it is actually the problems that you face during the experiment and nothing you could do about it. So for most of the students love to give this as the limitation. They love to state that there's not enough of value of, for example, value of H, measurement of H is not accurate. So, and the suggested improvement is that students should repeat the experiment and find the average. Is this limitation? So because this is actually not a problem because you should do that. You should repeat the experiment. If you want to repeat 10 times, then you should go about it. If you want to repeat twice and you want to repeat more than that, yes, you may do that. Nobody stopped you from repeating the experiment. So that is not a limitation. If you can solve it during the experiment, then that is not the limitation. Remember that. So I give you more example on that. For example, you are given a meter rule to measure a diameter of a coin. Hey, coin, this small little coin here, and you're given a meter rule, a wooden meter rule to measure the diameter of the coin. They're supposed to give you vernier caliper or micrometer, don't you think so? But you can do nothing about it because that's the apparatus that you are given. You cannot change it. You cannot simply change it like that. So one of the limitation is the measurement of the diameter of the coin would be very inaccurate. So your suggestion, use micrometer screw gauge or use a vernier caliper to measure diameter of a coin instead of a meter rule. So that is what we call limitation. That is what we call suggestion of improvements. So you definitely know that the meter rule is not a good apparatus to measure the diameter of the coin, right? So what can you do about that? You can do nothing about that, right? So suggestion of improvements, make sure you suggest something that is really, really realistic. I receive a lot of suggestion from students that how do you know whether the suggestion is realistic? Okay, let us see one example again here. So let's say one of the limitation is the air resistant. Let's say this is the plastic ball. So I am going to swing the plastic ball, and you know when you swing the plastic ball or you throw the plastic ball or something, you throw out the plastic ball, air resistant because plastic ball is moving. So therefore, air resistance might be the cause of the speed of the plastic ball to vary. Don't you think so? Something that is moving, there must be air resistance acting on it. So one of the improvements suggested by students, conduct the experiment in vacuum. My jaws drop immediately. How do you do that? How do we go to the vacuum? How do we go to the moon? Are you going to go to the moon or look around your lab? Do you have vacuum chamber? So I don't think so. So therefore, you cannot suggest that because this is unrealistic. How do you breathe? You need air to breathe, right? So that is not one of the good example for improvement. So don't do write that. So make sure that whenever you want to write for your limitation, make sure that you have a good improvement for that. And some extra tips that I would like to give you here, which not in my slide. So is that whenever you are lack of idea to write your limitations on your improvements, focus on whatever you are asked to investigate. For example, just now you should remember T is equal to KD, T squared is equal to KD. So focus on your measurement of T, focus on your measurement of D to give you some ideas. So how to make the measurement of T to be more accurate, how to make the measurement of D to be more accurate. So that is the limitation. But what is the problem? That you could not measure D or measure T as accurately as possible. So what do you do about it? And one more thing. So for limitation and improvement, there is a general limitations. So what is the general limitation? Two readings are not enough to draw a valid conclusion. Definitely. So because we need to take more reading to see the relationship, right? So that is one of the limitations. Memorize that. And the improvement, yeah, the general improvement is that take more readings and plot a graph. That is the keyword there. Plot a graph to see the relationship. That is one of the improvements. So all you need to do is just to think of 3 limitations and 3 improvements. That's all. So I hope this video helps. And please do subscribe to my YouTube channel for more tips, more shortcuts, more easier way to learn your physics in a fun way, etc. So if you have any doubts in physics or whatsoever, or any physics related question, and you have problem with that since a long time ago, please do comment below and I will make a video just for you. And please do subscribe to my YouTube channel, and I wish you all the best in your exam. Thank you very much for watching, and see you in my next video. Bye.